Okay, I'm on problem number 6 out of 8 for my 2007 final exam for algebra-based physics course, the first semester, and I'm just going to work through them. So I'm going to turn off my camera this time so you don't look at me from the side, and let's get to this problem. What is the weight gravitational force the Earth exerts on a 70-kilogram astronaut in space station orbiting 300 kilometers above the surface of the Earth? That's a good problem. Let's just draw a picture. I mean, this is something I actually covered in class, but this is, we'll call this R. We'll call that REarth, which doesn't matter. And then we'll just say this is FG. I'll leave it as a scalar. Okay. So you're thinking, oh, they're in orbit, they're weightless, but they're not. We can just use the universal law of gravity. The magnitude of this gravitational force is G, mass of the person, mass of the Earth, divided by, I do need the R of the Earth, divided by R squared. So in this case, R is going to be 300 times 10 to the third, that's meters, plus the radius of the Earth, which is 6.4 times 10 to the 6 meters. And then I need the mass of the person, and that's equal to 70 kilograms. The mass of the Earth is 6 times 10 to the 24th kilograms. That's what I put. So now I just need to put all this stuff into here. Okay, so this is a pretty straightforward question. I mean, I'll tell you right now, I'm going to do this in Python because Python's awesome. But when you do this, when students do this, they make mistakes with scientific notation and order of operations, especially when they put it in there. But in Python, it's pretty easy because watch this. Let's switch to Python. Okay, clear all this stuff. So let's put in my values. ME equals, I'm going to use the same value I have over here. 6 times 10 to the 24th. 6e24. RE equals 6.4 10 to the 6th. H is the altitude above. Let's call that 300e3, 300 kilometers. I think the space station is actually at 400 kilometers, but I don't really care. G equals 6.67 times 10 to the negative 11th. And so now let's just say FG equals G. Oh, I need the mass of the astronaut. M equals 70. So FG equals G times M times mass of the Earth divided by, if I want, I could do this. R equals H plus RE, and then do R squared. You know, and this was what's really great about Python is if I don't want to write that out down here, I can write another equation before that and substitute it in. It doesn't really matter. Python calculates lowercase r. It never prints it because I never told it to, and then I don't have to worry about it. If it's a complicated equation, break it into pieces, right? So now I'll just print this, FG. Oh, by the way, especially now, I do let my students use the calculators, Python as their calculator in class, in the test. If they want to bring their laptop and write a Python code, I trust them. I think the benefits outweigh them trying to cheat. Because I don't think it'd be obvious if they, I think it'd be obvious that they cheat. Let's do something else. Print M times 9.8. That's the weight on the surface of the Earth, just for comparison. So then I have 624 newtons in orbit, 686 newtons on the surface of the Earth. And that's it. That's the end of the problem. Is this a good problem? It's a little too easy, but I like to have a mix of difficult and harder problems. And again, these are 8 problems. They choose 7 in 2 hours. So I don't think I'd use this problem again, but it's the easy problem. And the thing is, if they did miss it, it could be because they had a calculator error, and I don't like that. I mean, it's still fair, but okay, we'll do another problem.